then today we are going to start. We are going to start on direct current circuits, so DC circuits. I've given us 2 weeks to go over this. We probably won't need the whole 2 weeks, and so we might get a little bit ahead, which would be great because we're going to lose some time in a week or two when we talk about the projects. But this is a really kind of nice start, and where the idea here is if you're going to build a circuit, you're going to want to know how much voltage is going to be across each of the elements of the circuit. You're going to want to know how much current is going through each of the branches of the circuit. And so this is kind of the basis of how you would figure this out. Now, those of you who are electrical engineers are going to do this better and faster than I will ever know how to do. So this is going to be like very basic for those of you who are going on to take like a circuit analysis class in your engineering departments. But it will have like just the basic knowledge of how and why those things happen. So far, so good. Okay. And let me let you know, your labs for the next couple weeks are really just going to be completely over DC circuits. So I've actually lined this up. I'm very proud of myself that I've lined this up right. So I would recommend paying attention to those labs. Okay, so let's if we have no questions, we can go ahead and get started. So I am sorry, let me. Over here, my notes are right here. Excellent. DC circuits. So DC circuits. So DC stands for direct current. And this is as opposed to AC circuits, where AC stands for alternating current, or alternating current behaves like a sine wave. It goes one way half the time and the other way the other half the time, which we will get to in many weeks. But a DC circuit means that you're going to flip the switch and current's going to start to flow through the circuit, and it's going to reach a steady state where it's just 1 amp or half an amp, and it's not going to fluctuate at all. Sound okay? Okay. So the thing that's going to provide that current are the batteries, and so we need to talk about batteries a little bit. Where how if I asked you to describe a battery, what's the first thing that you would describe about it? Or like, yeah, voltage, and we're going to get to positive and negative, but so far we've just thought of them as these like voltage providers. You know, this is a 6-volt battery, this is a 10-volt battery, and there haven't been that much difference between the voltage on our battery and like the voltage across a capacitor. However, there is a big difference between battery voltage and capacitor voltage, because in a capacitor, what makes that voltage is literally that there are electrical charges on either plate, and those electrical charges have potential, and when you add them all together, that's how you get the potential of a capacitor. A battery, though, it's not made up. Well, I mean, like technically everything's made up of charges, but it's not getting its potential, its voltage from these charges. It's getting them from some other mechanism, usually through some like chemical potential energy, like, you know, a lithium battery. The lithium has the chemical potential in it. So we put the battery voltage into this special case where we call it electromotive force, or EMF. Motive force, or EMF. Wow, that E just did not happen. EMF, electromotive force, where we talk about the electromotive force is like the chemical force that will push electrons through a circuit. So we think of this battery, a lot of people like to talk about batteries in terms of like a pump. So, you know, like a water pump pumps water from one place to another. You can think of a battery as something that pushes charge, pumps charge from one place to another. Just the same way that you would push water through a pipe. And so we measure batteries in their electromotive force, in their ability to push charge from one place to another. However, this electromotive force is not measured in newtons, it is measured in volts. So we have this really weird way of talking about batteries, because we want to separate them from capacitors. We want not to think of them in terms of the charge. We want to think of them in terms of how much charge they can push. We want to think about them like this pushing force. But since the way we're going to describe circuits as a whole is going to be in volts, the units of electromotive force are volts. So it's a roundabout way of saying, yes, we do measure battery voltage when we think about battery voltage, but I do want you to understand that that's not because there's a bunch of charge collected in this battery that's going to be expended. It's because there's this chemical potential energy that can produce a force that will push electrons. Sound okay? Okay. So absolute measure batteries in terms of voltage. When you see, a lot of times you'll see this EMF as just like a curly E. So when a battery, so on the diagram, when you see that curly E, that's the EMF that you're gonna see measured in volts, like the curly E will equal 6 volts or something. Also, so the next thing we need to talk about is how batteries have internal resistance. So batteries, being physical things, have resistance, just like copper has some amount of resistance. So like everything has some amount of resistance. Batteries tend to have a little bit more internal resistance than other things, but that's going to matter when we start putting current through them. So for example, if I have a battery and it's got some internal resistance to it, so I'm gonna like symbolize that by putting a resistor right next to it. It might be 6 volts here, and there might be a current going through here. I'll say 1 amp. But this internal resistance, maybe I have an internal resistance of like 0.5 ohm. Not a very big resistance, but you know, I have some resistance. When I measure from here to here, so, and remember that resistor is like part of the battery. So when I measure across the battery, I'll see this voltage jump. I'll see a plus 6 volts for the battery voltage, but then I'll see a voltage drop across that resistor. And the voltage drop across the resistor will go according to Ohm's law, V equals IR. So this will be the current times the internal resistance R. Does that make sense? And that's what you're going to read as the voltage across the battery. You're not going to read 6 volts. You're going to read 6 volts minus this voltage drop. And you might consider, what if so we started off with 1 amp. What if our current doubled? So initially, you know, we have 1 amp times 0.5 ohm So this is 6 minus 1/2. So we have 5.5 volts, right? What if we doubled our current? What if our current was all of a sudden 2 amps? What would our voltage battery be then? 5? I think I heard in the back there, right? 5 volts. And so I'm hoping you notice that the voltage that you're measuring across this battery, it's going to change depending on how much current's going through the battery. So depending on what you hook up to your battery voltage might drop a little bit, or it might drop a little more significantly. Does that make sense? Now, generally, you try to get your battery to be rated so that whatever you hook up to it, it won't significantly change the voltage across your battery. But you will have to take into account this into account sometimes. But luckily, the way you do it is just like this. You say, okay, I have a battery, and then you say, I've measured the internal resistance of my battery, and I'm just going to model that as like one little resistor in series with my battery. And so whatever other resistors or capacitors there might be in the circuit, you just add this little resistance of your battery onto them. Make sense? Okay. Excellent, excellent. Okay. Now, you probably noticed that I just said resistors in you add this resistor in series. And so the next thing we're going to do is we're going to talk about resistors in series and resistors in parallel, just like we did with capacitors. Because the idea will be eventually that, okay, I'm going to give you this circuit, and you're going to tell me how much current goes through each spot. And so you're going to need to know how the resistance works across each spot. So let's do this. We're going to start off with resistors in series. In series. And we're going to want to know the same thing. So we have some circuit with a bunch of resistors in it, say R1, R2, R3. And what we'd really like is to say, okay, if I was going to replace all 3 of those resistors with an equivalent resistor, what would that resistor be? Sound good so far? Okay. What we have to work with is Ohm's law. V equals IR. And so what we're going to want to do is we're going to want to characterize the voltages across each of these things and the current through each of these things. Okay. So just to be clear, the voltage of these batteries is the same. The wires are perfect wires. We're not expecting any resistance from the wires. And really quick, can someone tell me what the definition of series is?
It's mathematical definition, I guess, or like you want this to go to
Just give me the
wires that are connected directly to. So are these wires that are resistances?
Wires are resistors. So like, and we'll do resistors because we're talking, but right, resistors that are connected directly to each other. So there's no branching paths, right? Okay, so resistors that are connected directly to each other so that everything that goes through one has to go through the other. Through the other. Wow, I should have here. Let me put this over here. series. Everything that goes through one has to go through the other. Goes through one has to go through the other. Okay, excellent, excellent. So with that in mind, what can you tell me about the current through R1, R2, and R3? All the same, because they're connected in series. The current doesn't have the choice. If it goes through R1, it has to go through R2. So the current in 1 has to equal the current in 2, has to equal the current in 3. Whoosh. And so we're just going to call that I. We don't need a subscript on it because it's all the same. Also, since this is an equivalent resistor over there, the current through that equivalent resistor needs to be the same as the current through my first circuit. Okay, so that's current. What about voltage? Can we say the voltage is the same across each 3 resistors? No. Yeah, so yeah, there's like, if they're all the same resistors, sure, but if they're different resistors, maybe they'll be different. So we can't say the voltage across the resistors is all the same. Is there anything we can say about the voltage across the resistors? Oh, okay, the voltage of the battery. So if we add up all the voltage across the resistors, I like that. So like, yeah, if we start here at 6 volts and we know we're going to end up at 0 volts, whatever the voltage drop across that, plus the drop across that, plus the drop across that, had better get us down to 6. And it could be divided up however it wants to be divided up, but it needs to add up to 6. And of course, if we go to our equivalent resistor, the voltage across the equivalent resistor needs to be the same as well, because I only have the one resistor in that equivalent circuit. Is that okay? Okay. Almost there then. So if what I'm looking for is R equivalent equals some combination of R1, R2, and R3, I have this equation here. And so I'll just take each of these and I'll say like V1 equals I1 times R1 and V2 equals I2 times R2. Okay, so I have the voltage of the battery equals V1, so I1 R1, V2 I2 R2, V3 I3 R3, and that's of course the equivalent voltage, so I'll just call that I times the equivalent resistor. Okay, and I put subscripts on my I's, on my currents. Did I need to do that? Excellent, because yeah, series, they're the same. Okay, given that, what can I do with all these I's in this equation? I can factor them out and cancel them, right? So I'll just divide both sides by I. And I will end up with a very nice equation where my equivalent resistance equals R1 plus R2 plus R3. If I had added a 4th resistor in series, would I have just added it on to the end here? Right, so I could add as many resistors in series as I like. And I would then shorthand this equation to say my equivalent resistance is just the sum of all my resistors. What sort of units should I put on my resistance? Ohms. Okay, and I'm just going to note that over here that these are ohms. we did a really similar derivation for capacitors. Was this the equation we got for capacitors in series, or was this the equation we got for capacitors in parallel? Parallel. So yeah, so for capacitors in parallel, we found that you can just add up the capacitances. So I do want to make sure everyone sees the difference, because they're going to flip when we do resistances. When we do resistances, when they're in series, you just add up the resistance versus parallel. Okay, that one, are y'all happy? Okay, then let's do parallel. And so what's a good definition for parallel? Okay, so the current gets split between the resistors. So current that goes through one will not go through the other. Nothing that goes through one can go, current that goes through one will not go through the other. Through the other. And this is like a total exclusion sort of thing. So nothing that goes through one can go through the other. So you can't say that part of one of the things goes through the other. It's your current either goes that way or it goes that way. Sound okay? Okay. Okay, so parallel. So we want to go through the same thing. And at the end of the day, we want to say, there's my R1, there's my R2. If I put the same battery across a circuit with just one resistor, so that the current going through these scenarios, I need everything just to act the same. Sound okay? Okay. We still are going to be using Ohm's law, so V equals IR. So we need to talk about the voltages and the current. Now, for series, we were able to say that the current would be the same between R1, R2, and R3. Can we say that here? Can we say the current will be the same in R1 as it is in R2? No. I like no. Because the whole point of parallel is the current gets split. And if one of these resistors is a lot smaller than the other resistor, it's going to draw a lot more current than the other one. So we cannot say that the current going through R1 will be the same as the current going through R2. Is there anything that we can say about the current? In particular, is there something we could say about the current going through R1, the current going through R2, and the current going through this equivalent resistor? We're gonna total it up. Okay, and you'd be right, because over here in this equivalent resistor, the current going through the resistor is going to be the same as the current going through the battery, right? So we can do that there. For this to be equivalent, the current through this battery needs to be the same equivalent current. And since I can't like create or destroy current, whatever goes through I1 plus whatever goes through I2, that'll be what goes through the battery. So I1 plus I2 is whatever is going to go through the battery. Okay, so there's my currents. What are my voltages? Can I say something about the voltage across R1 versus the voltage across R2? The same, different, we don't know, needs to add up to something. What do you think? We're not sure. Okay. Yeah. So yeah, so if it starts at 6 and ends at 0, it's at 6 until it hits there, and 6 until it hits there, right? So yeah, so they need to be the same, right? Does that make sense? And of course, the same thing would be over here. If this battery is the same at 6 volts, the voltage across that resistor will be 6 volts. So we can say V1, the voltage across resistor 1, equals V2 equals V equivalent. Okay. Okay, if that's good, we're almost done here. We need to use this to figure out some resistances. So what we're going to do is we're going to take our Ohm's law and we're going to say I equals V over R. And then here we're going to plug in V1 over R1, V1 over R, V2 over R2, V equivalent over R equivalent. And then you're going to tell me something about these voltages. Equivalent V of the battery over R equivalent. Okay, and what are you going to tell me about these voltages? They're all the same. So we can cancel them out. So we end up with a very familiar equation. 1 over R equivalent equals 1 over R1 plus 1 over R2. 1 over R2. If I had a third resistor in parallel, I would have just added it on up until some nth resistor. And so, of course, we can write this as the summation of 1 over R sub I. We're going to always remember then when we're adding up 1 over R's that we need to invert it at the end because we're not looking for 1 over R equivalent, we're looking for R equivalent. And we're going to remember that this equation only works for series resistors in parallel. And so before we use it, we need to figure out whether our resistors are in series or in parallel. Okay. Everyone okay with this so far? All right. Well then. Yeah, it absolutely is. It can be a little confusing. So yeah, just keep it in your head. If we're happy here, let's do a problem. Okay. So what I want to look at is I want to look at what is this? This is number 9 on your homework. I want to look at number 9 on your homework. Is we have this. So I have a battery. I have it hooked up to 3 resistors, R1, R2, and R3. Like here. And I have this switch where I can, if I open the switch, current can't get through that branch. And if I close the switch, current can get through that branch. And I want to know, when I close this switch, does the overall resistance increase or decrease? Overall resistance of this circuit increase or decrease? Does that make sense? Okay. So let's talk about this. I want to do the math first, and then I want to talk about some concepts. So let's do the math. Let's find the equivalent resistance of this when the switch is open. Okay, when the switch is open, does R3 even matter? No. Okay, so when the switch is open, that doesn't even exist. So we just need to look at R1 and R2. And would you say R1 and R2 are in series or are they in parallel? Series. Okay. Would you say that? So like, if I close the switch, would you say that R1 and R2 are in series? No, right? So just by having that switch open, we're changing the geometry of this circuit. Okay. Okay, so switch is closed. I have a battery, I have R1, I have R2. I'm not going to tell you what R1 and R2 are equal to, but what would the equivalent resistance of this circuit be? R1 plus R2. They're in series, you just add them together. Okay, now let's, oh, I'm sorry, this is when the switch is open. I'm sorry. Clearly. Now let's close the switch and let's talk about what would happen. So if I close this switch, you just told me that I can't consider R1 and R2 in series anymore. Two, three. So how would I find the equivalent resistance of this circuit now? All right, so I do R2 and R3 in parallel, and then I do that in series with R1. Okay, so in parallel, I have to use this guy, right? Over R3. And I'm gonna go ahead and find the common denominator, R2 over R2 times R3, because that'll make this easy to invert. So R2 times R3 over R2 plus R3. Sound good? And so that will R2 3 like that. And then, as you guys told me, I'm gonna put this in series with R1. Okay. So, and this is closed. So looking here, when this is open, my equivalent resistance is R1 plus R2. When it's closed, my equivalent resistance is R1 plus R2, R3 over R2 plus R3. Okay, which one's bigger? Any idea?
Like stronger resistance.
Yeah. So let's look at this. So they both have an R1 added. So we're really just comparing this to that, right? Okay. Okay. Well, let's plug in some numbers. Let's set everything equal to 1 and see what happens. It's a solid choice. So like this would be 1. And over here I'd have 1 times 1 over 2. So open stronger. And that's going to be true always. Oh, so open has more resistance than closed. And so let's talk about why that is true. So because apparently this setup has more overall resistance than this setup, even though we've added an extra resistor, right? And so here's where I want you to think back to last week when we were talking about what makes something resist current. So remember we had this equation, right? What did the L stand for? The length, right? So we had like the length of a wire. What did the A stand for? Excellent. Cross-sectional area like that. So we said the longer the wire, the more resistance it will have, because each little section has some amount of resistance. And so when you add all those resistances, you get a greater overall resistance. But then we said, well, if your wire is wider, that actually decreases the resistance. And one thing we talked about was pathways, right? So the wider the thing is, the more pathways an electron would have to get through here. And so when I added that resistor in parallel, what happened was we added a pathway for the current to go through. So basically we doubled the area that the electrons had to get through. Popular analogy is highway lanes. So like if you only have one highway lane, you're going to have a lot of traffic backed up and everything's going to be moving slowly. But as soon as you open a second lane, then you have two places for cars to go and you can move a lot more cars through more quickly. And that's what we're doing when you're adding elements in parallel. You're just adding pathways for the electrons to get through. And even just looking at this equation, I'm hoping that you guys see that the more things that you add in parallel, the closer to zero your equivalent resistor is going to get. Okay, and let's talk about why you would never want to do that. So if I have this battery here, and I have my first resistors, so there's resistor 1. It's got, whatever the voltage of the battery is across it. So it's got a certain amount of current going through it, right? VBAT over R1. I'm going to add another one. So that's VBAT over R1. I'm going to add another resistor. So it'll have some current going through that. I1, I2, VBAT over R2. So looking at this, I have current going through resistor 1. I have current going through resistor 2. What has happened to the current going through my battery? It's increased, right? Because I can't just have current going through the resistor. The current has to go make that entire loop, right? So the current going through the battery, before I added that extra loop, it was just I1, but now it's I1 plus I2. So my current through the battery has increased. And if I add a third resistor, the current through the battery will increase again, right? And so as I'm adding more loops here, what I'm doing is I'm increasing the total current that's going through the battery. Will that be okay forever? And what's going to happen to tell me that it's not okay? How will I know when I've added too many things too many branches in parallel to my circuit. Say again? I will blow a fuse. And I will be lucky if I do that, right? Because the thing that'll happen if I don't have a fuse is my battery is going to start heating up and I'm going to start a fire, right? Because yeah, and if you think about your kitchen, is your kitchen wired in parallel or series? So each of the outlets in your kitchen, do you think they're wired in parallel or in series? Parallel. And you might think, well, you know, I know it's parallel because if I unplug my blender, my toaster doesn't turn off, right? Where in series it would. So you have everything in your kitchen wired in parallel. And what happens if you turn on too many things in your kitchen? You blow a fuse, right? Because what you're doing is every time you plug something in is you're drawing that much more current. And whatever wire is providing current to your kitchen has to carry all of it all at once. And so if you don't have that fuse in place, it will just start to melt and it will burn down your house, which is why you add the fuse. And for example, like in this diagram that we have here, where would you want to add the fuse? What would you want to add a fuse here or here? The second one? Because here, if it breaks, current to the entire circuit's cut off, right? If this breaks, just current to that part is cut off. And if you want to, if you're to the point where you're breaking the current, you want to just shut it down. Okay. Okay. So I'd just like to point out to you that here are two ways that you might want to hook up things where sometimes parallel is useful. Where parallel is useful if you want to have multiple things that you can turn off and on at once. Sometimes series is useful, where if you want to have one element that affects all the other elements, you want that in series. Sound okay? Okay, excellent. This looks good. What do we need to do next? We got series, we got parallel. Ooh, okay. Sorry, I'm catching up. Went through a lot of notes apparently. There we go. Sorry, gonna think this through really quick. Actually, we're gonna keep doing this problem because before I do Kirchhoff's loops, I wanna talk about how you would deal without Kirchhoff's loops. So so now with this problem, we have an equivalent resistance when the switch is closed. We have an equivalent resistance when the switch is open. What I'd like to do now is I'd like to compare the current going through the battery in each of these cases. Okay, so in this one, I'll have some current. I'll call it IO for I open. I'll call it I open. Here, I'll have a more complicated current because it'll split off here and it'll come back here. But when it hits the battery, it'll have some current. If I wanted to find these currents, I'm given the battery voltage, I'm given each three of these resistors. How could I find the current through the battery? What would I do? I like that. I would go to Ohm's law, right? Was it too easy of a question or too hard? Too easy. Okay, okay. Trick question. No, it's never a trick question. Okay, so if I want the current through the battery, I need to set that equal to the voltage of the battery, and I need to multiply by the total equivalent resistance. Because the idea behind equivalent resistance, right, is that I've made a circuit that's doing the exact same thing, but with just one resistor. So that means for the open one, if I want the current through the battery, VBAT, I think I used curly E over R equivalent. Sound okay? And for this guy, still doing closed, it will be curly over R equivalent, where R equivalent is much, much more complicated, right? Okay, so I have these two currents. One's pretty straightforward, one's a little less straightforward. And that's what the current through the battery is going to be. Now, if I wanted to talk about each element, so like if I wanted to think about R1, R2, and R3, will the current through R2 be the same as the current through the battery? Let me hop back over to my diagram here. Okay, will the current through R2 be the same as the current through the battery? I like the no, right? How about R1? Okay, so just knowing that knowing the equivalent resistance and the battery voltage, we can figure out the current through the battery, we can figure out the current through R1. What if I told you that R1 and R2 have the same resistance? Would you be able to tell me the current through both of them then? Like if R2 equals R3. Yeah, what would you say about it? Like that, you could. So yeah, you could do an equivalency. Can you make a? Can you say I2 is just equal to I3 in this case?
Yeah.
Okay. So if like they're the same, then the current should split up equally. What if R2 is twice as big as R3? Could we say something about the currents then? We could, and let's justify this. So if this is true, then the current through I2 will be half the current through I3. But let's justify this then, and I'm at this point I'm going to start making up numbers. So 1 ohm is a good place to start there. Let's say that this battery is 6 volts. Let's not say this battery is 6 volts. That's going to be a hard number to justify. Let's say the current is 6 amps. That'll be an easy number to justify. So whatever the battery voltage is, the current is 6 amps. Can you tell me the voltage across R1 at that point? It would be 6, right? Because we can still do V equals IR. I'm going to pop open another thing. So we can still do V equals IR, and we can do it across each element. So if the current going through here is 6 amps, then the voltage across 1 will be the current times R1, 6 amps, 1 ohm, 6 volts. Okay, now let me say, now I'm gonna say, what if this battery 6 had 12 volts on it? If this battery had 12 volts on it, and we know the voltage across R1 is 6 volts, what can you tell me about the voltage across R2?
If you change the voltage to 12, would the current be 12 for R1 as well?
Yeah. Let me just tell you, like, the things that I right now, the current through this battery is 6 amps. R1 is 1 ohm. I'm not going to tell you what R2 and R3 are quite yet. And the battery voltage is 12 volts. And so if the battery voltage is 12 volts and the voltage across R1 is 6 volts, what's the voltage across R2? It would be 6. And I like that, because you guys, I think, are tracing your path around, right? So if you start off at 12, you lose 6, so you should be 6 right here. Right here, you need to be at 6. And you need to get back to 0 by the time you hit there. So that means you need to drop to 0 to make it back. So the voltage across R2 will be 6 volts. What about the voltage across R3?
0.
Six, right? Because just like there's a pathway through R2, there's a pathway through R3.
Does it not split though? Like
So the current splits, but the voltage does not. So this is 6 volts. Okay, so, and this is going to come back. This is something we saw back here, where the voltage across each of the branches was the same. Here we have the same idea. The voltage across since it branched out, the voltage across R2 and R3 are the same. Okay, now if I told you that R2 was, I don't know, R2 is 2 ohms. Let's say R2 is 2 ohms. Can you tell me what the current through R2 will be? 3. Good. 3 what? Amps. I heard it. Because 2 times 3 is 6, right? Okay. And let's set R3 to half of that. So R3 is 1 ohm. Now what's the current through R3? 6 amps. Okay. Excellent. Excellent. This is what I wanted to see. And so just what you guys predicted, if R2 is double R3, I2 will be half of I3. Because since the voltage across them is the same, I'm hoping you see that the smaller resistor is going to pull more current, and the larger resistor is going to pull less current. And the common analogy that you will see people use is you see this analogy of water running down a hill, where the height of the hill would be like the voltage. So that tells you like how much energy you have to start out with. And then as water goes down the hill, it could take different pathways. The pathway that goes down the steepest will draw the most water. The pathways with the most obstacles will draw less water, right? And so here, the pathway that has the most resistance, you'll still have some current through it, but it'll be a lot less than the pathway that has the least resistance. And everyone looks pretty happy with that idea. Okay, excellent, excellent. So let me tell you, that is one way to solve a circuit. Find the equivalent resistance. That lets you find the overall current, and then you can kind of just step through saying, okay, I know the voltage here, so I know the voltage over here, and so that means the current here has to be like this, and you just step through each part. There's occasionally you won't be able to do that. And also, there is actually a more straightforward way to look at that. And that will bring us to Kirchhoff's rules. Okay, so Kirchhoff has two rules. Basically, you use it to analyze circuits. It's conceptually simple. It will always give you an answer, and it is algebraically difficult. This is where engineers always pull out their graphing calculators and put things into matrices. But let's talk about them. So Kirchhoff's rules, there's two of them. We have the junction rule, where anytime you have a junction, and junction is any split. In fact, you don't even have to say split. You can just be even more simple than that. But basically, any spot on a circuit, the current in has to equal the current out. So like if I just have a straight wire and I pick a spot on it, the current into that spot has to equal the current out of that spot. That would be the Bourne example. But if you have an actual junction where you have a split, the current into that junction, and I'll call it like I'll call this current 1 and 2, has to equal the current out. So in this case, IN would equal I1 plus I2. And that's just like a conservation of charge sort of thing, where if some amount of charge goes into a spot, the same amount of charge has to leave that spot. You can do this two ways, because if these two things come back together, then the current going in to that spot needs to equal the current going out of that spot. Sound okay? Hopefully. Okay, so that's the junction rule. Then we're going to have the loop rule. And so the loop rule says that any loop you make, any closed loop you can make, when you add up all the voltage drops and all the voltage gains, they need to add up to 0. So looking at this, so like if I have a very simple circuit like this, and I start right here. As I go through this battery, I'm going to gain the voltage of the battery. I keep going through, I hit this resistor, and I go across this resistor, I'm going to lose the voltage across the resistor. And then when I hit back where I started, I know that whatever voltage I started at, that voltage needs to be the same at the same spot, because I'm at the same spot. So whatever adds and losses, they need to add up to 0. Because if this is at 0 volts when I start going around, it needs to be at 0 volts when I come back to it. Everyone okay with that? Okay. Now this one can get tricky, because any loop at all needs to add up to 0. So for example, if I have a more complicated situation, whoosh, wow, like that, I could make a loop that just goes around this one little spot, and the whatever is going around that one little spot also needs to add up to 0. Because if I start here, I have no idea what the voltage is going to be right there, but if I go around this loop, I need to be back at that same voltage. Does that make sense? So whatever voltage across R2 plus voltage across R3 is, they need to add up to 0. And you might be looking at that and you might be saying, how can you add two voltages together and get 0? And clearly you're going to tell me that one of those voltages needs to be negative, right? And so we need to talk about how you figure out when a voltage is positive and when a voltage is negative. And we're going to combine this with our loop rule. So let's do the simplest because I don't have enough time to do less simple. Okay. Simplest circuit. R1, battery. Whenever you do this, start with setting the directions of the currents. Now, on a simple circuit like this, you're going to be able to pretty much tell which way the current is going. But it doesn't matter which way you set it as long as you're consistent about it. So I probably do have time to do it 2 ways. So let me say, let's set it this way first. Okay, if you have any junctions at this point, you write down your junction rule. So you say, okay, all the current into this junction equals all the current out of this junction. We'll do one of those on Thursday. Then you do your voltage rule, where you pick a spot and you go around the circuit. So I'm going around the circuit. When you hit a resistor, and if you're going with the current across the resistor, you drop that voltage. So with current across resistor, you drop that current. Okay, you go across the resistor, you hit the battery. If you're going from the negative side of the battery to the positive side of the battery, you're going to gain that voltage. So you would add that. So from negative to positive, add voltage. And then once you hit the spot where you started, that needs to add up to 0. Okay, so for this problem, I don't think anyone is going to be surprised that this will give you the voltage across the battery is the same as the voltage across the resistor. Okay, sounds good. But now, let us go the other way. What if I had set the current to be that way? Okay, so let's look at this. I'm again going to start here. I'm going to start going around, but then I'm going to hit this resistor. And now I'm not going with the current, I'm going against the current. And so I'm going to add it. So if you're going against current across the resistor, you're going to add. Okay. I go through, I hit my battery. Now I'm still going negative to positive, so I'm still going to add across this battery. Do that, equals 0. And then you're going to say, wow, okay, so then I come back to where I started, so I set it equal to 0. And now from this one, what I'm getting is VBAT equals negative V1. And you might say, well, this is contradictory. And you wouldn't be entirely wrong here. But let's see what is going to happen, because what we're really doing is we're really solving for current, right? That's what we want to know, the current in each spot. And now the current will be that current times R1. Over here, current times R1. And notice that the second option is going to give us a negative current. So the first option, when we had put the current in the correct direction, we get a positive answer. The second option, when we put the current in the wrong direction, we get a negative answer. And what that negative sign is telling us is that we set the current to be in the wrong direction. Does that make sense? Now let me tell you, all of your equations will work out. You'll just end up with a negative answer for your current if you set it in the wrong direction. And then at the very end of the problem, you can be like, oh, look, it actually goes to the right, not the left. And that'll be fine. That's not a problem. That's just, you have an extra minus sign. Is that okay? Okay, I want to do this one more time, going around this loop. And then, no, I don't actually want this. Okay, and we'll set the current to be the correct direction. But now I want to start here and go that way, just so we can see what it looks like. So as I go down through the battery, am I going to add that battery voltage, or am I going to subtract it? I like to subtract. So here, when we went negative to positive, we added the voltage. And if you think about that, that makes sense. Like we're starting at 0 volts, we're going to 6 volts or something. So if we start at 0 and go to 6, we should add that voltage. But if we're going the opposite direction, if we're starting at 6 and going to 0, we should subtract the voltage. You look a little unhappy with that. I am, okay, I'm so glad I did this. You are still going against the current. But for the battery voltage, it doesn't matter how you set the current. It just matters whether you're going from positive to negative or negative to positive. So this will give you a negative battery voltage. And then as you're going across here, now we're going to hit this resistor, and we're going against the current. So are we adding or subtracting that? Adding of the resistor. We go all the way around, we get back to where we started, and we say it adds up to 0. And so now we have V back equals positive VR. And so for this one, we definitely will get a positive current. And that's good because our current was set to be in the correct direction. Okay, sound okay? All right, I'm gonna start off next class with a complicated Kirchhoff's loop, and we'll work through that and talk about how to set up those equations. But those are the basic rules. Man, I didn't have my chat on. Is everyone online okay? I hope you guys weren't talking the entire time. Okay. See you on Thursday. It was great talking to you.